Hello, welcome back, everyone. We have made it out of Chapter 9 on viscosity, and today we are going to cover Chapter 10 in Fundamentals of Inorganic Glasses, which is devoted to the topic of thermal expansion in glass. We will cover what is thermal expansion, how do we measure it, what are the different types of thermal expansion, and how does the thermal expansion coefficient vary with glass composition. So let's dive into it. Going back to our favorite figure here, the volume temperature diagram. Of course, we use this in Chapter 2 to see how we can quench a liquid into the glassy state. One of the other important things about this diagram is the slope here. If you look at any of these phases, whether it is a glassy phase, the crystal phase, liquid, or supercooled liquid, there is some slope here to the volume temperature dependence, and therefore the derivative of this volume with respect to temperature at constant pressure can be used to define the volumetric thermal expansion coefficient, which is given by this letter beta. The volumetric thermal expansion coefficient is 1 over the volume of the system times the change of the volume with respect to temperature under constant pressure conditions. And this is important because it is telling us how much the glass shrinks upon cooling, or conversely, how much it expands upon heating. Now, the volumetric CTE is defined here as beta. It is more common to work with a linear CTE, where instead of a change in volume with respect to temperature, we deal with a change in length of the sample per unit temperature. So the linear CTE alpha is defined as being 1 over the length of the sample times the change in length with respect to temperature under constant pressure conditions, so isobaric conditions. And the linear CTE for an isotropic material like glass is related to the volumetric CTE as 1/3 of beta. Now, the typical units that are used to express CTE values for glassy materials are 10 to the -7 per degree C. And this is just a convenient unit because the thermal expansion coefficients for glass tend to be quite small. For a lot of other materials like metals and polymers, the units are usually 10 to the -6 per degree C, or ppm per degree C. But in the glass science community, it is conventional to express the numbers as 10 to the -7 per degree C because of the small values that are involved. How do we measure the thermal expansion coefficient? The standard way to measure the CTE is through dilatometry. This shows a schematic diagram of a dilatometer. The dilatometer consists of a furnace that controls the temperature of the sample as a function of time. The sample is placed in the middle here next to a reference standard, and then there is a push rod that pushes against the sample, and this measures the expansion of the sample as the temperature increases. So the way this works is that the specimen is held against the flat wall of the measuring system, and it pushes on a horizontal spring-loaded push rod upon heating. The change in expansion relative to either the system tube itself or relative to a second push rod against a standard specimen is measured using this LVDT, which is a linear variable differential transducer. So what this gets us is the expansion of the sample as a function of temperature, and a typical dilatometer curve is shown here on the right, where this shows the linear strain on the y-axis. This is the change of length divided by the initial length, and this is a function of temperature. And what we see, of course, is that if we start off at low temperature, say room temperature around 20 or 25 degrees C, and then heat up the sample will expand as the temperature of the system increases. And the derivative of this curve is what will give us the thermal expansion coefficient. We can also see that there is a difference here between well-annealed glasses, which, for example, is shown on the solid line, versus rapidly cooled glasses shown by the dashed line. For rapidly cool glasses, they show this turnover here at relatively low temperatures. This is because for fast cooling rates or high fictive temperatures, the glass is further out of equilibrium, so it has a greater thermodynamic driving force to equilibrate, and it also has faster kinetics of the relaxation process because the non-equilibrium viscosity of the faster cooled glass is quite a bit lower compared to the viscosity of the well-annealed glass. As a result, there can actually be some shrinkage of the sample due to relaxation as it tries to approach the metastable supercooled liquid state. And so even though at low temperatures where we are well below the glass transition region, the well-annealed and rapidly cooled samples may strongly overlap, indicating similar values of thermal expansion coefficient in the glassy state. As we approach the glass transition region, there can be a rather large departure between samples based on their differences in thermal history. The other thing you'll note is that when you get to temperatures a little bit above the glass transition temperature, we reach this so-called dilatometric softening point labeled as T sub D. This is where the sample in the dilatometer starts to kind of sag under its own weight due to the softening of the sample. And this sagging is in response to gravity. You'll want to make sure that you turn off the dilatometer at this point, otherwise you'll end up with a molten mess in the dilatometer, which nobody wants to deal with. The other thing to note is that as you're heating through the glass transition region, you'll note that there is a pretty significant increase in slope and going from the glassy state, which you can see here as a lower slope, compared to the liquid state, which has a much steeper slope. And the reason for this is that when we are in the liquid state, we have both vibrational and configurational degrees of freedom active, so that we have both vibrational and configurational contributions to the thermal expansion coefficient. If the liquid is cooled below the glass transition range, the configurations have essentially frozen in. And so that contribution to the thermal expansion coefficient is lost, and all that we have left is the vibrational part of the CTE. And so that vibrational piece is what is represented here at low temperatures in the glassy state itself. So this rapid rise in the expansion marks the onset of the glass transition upon heating. This curved hook downwards here, this dilatometric softening point, is an artifact of the measuring technique because of the slumping of the sample, softening under its own weight. This is an apparent contraction, which is not actually a contraction of the sample because it's just slumping. And this occurs at viscosities around 10 to the 9 through 10 to the 10 Pascal seconds. That temperature is called the dilatometric softening temperature and is designated as T sub D. What are the thermal expansion coefficients of some typical glasses at room temperature? Fused silica has one of the lowest thermal expansion coefficients of known glasses. Its CTE at room temperature is about 5.5 times 10 to the minus 7 per degree C. The coefficient of thermal expansion of germania, even though it has a structure that is very similar to the structure of silica, it has a much greater anharmonicity to the bonding due to the larger germanium cation compared to silicon. And as a result, its CTE is quite a bit higher. It is 77 times 10 to the minus 7 per degree C. And for B2O3 glass, it has an even higher CTE. There are fewer bonds here per atom because of the trigonally coordinated boron, and each of those bonds is fairly weak, and this gives a larger thermal expansion coefficient of 150 times 10 to the minus 7 per degree C. Now, interestingly, if you look at very low temperatures, this is going down to temperatures that are getting close to absolute zero temperature. Note that the numbers here are expressed in units of Kelvin. What you see is that the strain is vanishing in the limit of zero temperature, and that's because the CTE must approach zero in the limit of zero temperature, just as the heat capacity must approach zero in the limit of zero temperature. But you can see some interesting behavior here where some glasses like B2O3, for example, have positive values of the thermal expansion coefficient, in other words, positive slopes here, even at low temperatures, whereas other systems can show an initially negative CTE at very low temperatures, followed by a turnaround towards positive CTE. And so this is some fairly interesting behavior that can occur in glassy systems at extremely low temperatures. Now this is table 10-1 in the book. This shows the thermal expansion coefficient of some commercial glasses. For soda lime silicate, the thermal expansion coefficient for a normal soda lime silicate is about 93.5 times 10 to the minus 7 per degree C. This is very similar to a potash soda lead glass, also 93.5, and a potash soda lead, which is 89.5. Aluminosilicate glasses and borosilicate glasses can span a wide range. The ones shown here have significantly lower thermal expansion coefficients compared to soda lime silicate. Borosilicate glasses, at least the ones that are normally commercialized, have thermal expansion coefficients that are usually in the 30s times 10 to the minus 7 per degree C. And of course, here is fused silica at 5.5 times 10 to the minus 7 per degree C. Now, when alkali modifiers are added to silica, you can see what happens to the thermal expansion coefficient upon addition of lithium. There is a steady increase of CTE. If you use a larger modifier like sodium, it is also a steady increase, but at an even higher rate compared to that of lithium, and potassium is even higher. So in any of these cases, the alkali are acting to increase the coefficient of thermal expansion coefficient because they are converting bridging oxygens to non-bridging oxygens. That breaks up the connectivity of the network and gives the glass more degrees of freedom in order to expand. And if you have larger modifiers going from lithium to sodium and then to potassium, then those modifiers take up greater space. They've got weaker ionic bonding to the non-bridging oxygens, and that just leads to a progressively larger CTE in those cases. Here you can see this is the strain times 10 to the minus 4 as a function of temperature for different glasses with different levels of silica. And what you can see is that you've got steeper and steeper slopes, meaning larger and larger CTE values as you go lower in silica. So silica, SiO2, has one of the lowest CTEs of any known glass at 5.5 times 10 to the minus 7. And so for most glass compositions, if you lower the silica, the CTE tends to go up. Of course, one of the most interesting things in glass science is the boron anomaly. When we add modifier ions like alkali oxides to borate glasses, initially the connectivity of the glass network increases as trigonal boron is converted to tetrahedral boron. Then afterwards, there will be a formation of non-bridging oxygens. So upon initial incorporation of alkalis, the connectivity of the network increases. That actually causes the thermal expansion coefficient to go down. And you can see here that it goes down the most for the smaller alkalis because they would have the highest field strength. And the effect is less for the larger alkalis like rubidium, for example, because it's so huge. But then after the number of tetrahedral boron is maximized, continued addition of alkalis creates non-bridging oxygens, breaking up the connectivity of the network, and that causes the thermal expansion coefficient to go back up. And so unlike silicates that always showed kind of a monotonic trend of thermal expansion coefficient with alkali content, with borate glasses, because of the boron anomaly, first the expansion coefficient decreases and then it turns around and increases, reflecting the two different mechanisms that modifiers can play in borate glasses. Now, one of the most interesting glasses from the point of view of thermal expansion coefficient is ULE glass, or ultra-low expansion glass. Ultra-low expansion glass is designed to have a CTE of 0 and also a CTE slope of 0 around room temperature. And this is obtained by adding titania to silica. And you can see the curves here show the addition of the different amounts of titania to fused silica. So adding 3.42 weight% of titania, this brings the CTE downward. If you add 6 weight% of titania, it comes down even more. And if you add 7.4 weight% of titania, you get not only a zero slope here, so indicating a zero CTE, around room temperature, but also a zero slope of the CTE curve. And so that particular composition, plus or minus a little bit in weight% of titania, is what's called ultra low expansion or ULE glass. ULE glass is used throughout the lithography industry because the material needs to be able to heat up without changing its dimensions. ULE is also useful for telescopes in space and for mirrors in space because they are subject to widely varying temperatures, and ULE ensures that there aren't any dimensional changes that could distort the optics of the device in response to those temperature changes. Now, what is the atomic origin of the coefficient of thermal expansion? As you have probably learned in your Introduction to Materials Science course, the vibrational part of thermal expansion coefficient can be traced down to the anharmonicity of the vibrational modes, where if you look at a typical potential energy well for two atoms bonded to each other, what we see is that in the limit of zero separation distance, the potential energy would go to infinity. This is due to Pauli's exclusion principle because you can't have two atoms sitting on top of each other. So the energy goes to infinity and the limit of R going to zero. In the limit of R going to infinity, the energy goes to zero because if two atoms are separated by infinite distance, there's no interaction between the two. So in that large separation distance limit, the energy of the bond goes to zero. And in between the two, there is a well that has a well depth to it. The positioning of this well depth defines R0, which is the equilibrium separation distance between two atoms at 0 Kelvin. And then the well depth here gives the bond strength, or the energy that is associated with the bond. Now, if you were at 0 Kelvin, at absolute zero temperature, the atoms would be sitting at this equilibrium distance. But as we increase the temperature of the system, we're adding more thermal energy to the system, and that allows the vibrations to kick in, and the atoms will vibrate around this asymmetric and harmonic potential energy well. And so there'll be vibrations around here. As you increase the temperature, the magnitude of the vibrations becomes greater and greater and greater. Now, because of the lack of symmetry of this potential energy well, since it's going to infinity on one side and going to zero on the other side, if you take the average separation distance for any level of temperature, that average separation distance is given by this dashed line, and it is actually increasing as the temperature of the system increases because of the asymmetry of this well. So what this means is that as the temperature of the system is increasing, the average separation distance between atoms is also increasing following this dashed line. And therefore, the system is expanding as a function of temperature, and the degree of that expansion is governed by the degree of anharmonicity of the potential energy well. So a greater anharmonicity means that we've got a greater increase of the separation distance with temperature, which means that the system would have a greater vibrational contribution to the thermal expansion coefficient. The way to get rid of this would be, what if you had a perfectly harmonic well? In other words, what if this were a parabola instead of the shape shown here? If it's a parabola, then the average separation distance would be the same independent of temperature, and the vibrational part of the CTE would vanish. Now, the vibrational part of the CTE is what is dominant at low temperatures, whether it's the low temperature crystal state or the low temperature glassy state. The vibrational part is the key part of the CTE at low temperatures. However, if you take a glass and then you heat it up through the glass transition region to get into the supercooled liquid or liquid state, there is a second contribution to the thermal expansion coefficient, and that is due to the configurational contributions to the CTE. And you can see that in the change in slope of the volume temperature diagram. See here in the glassy state, it has a lower slope, and that's because only the vibrational modes are active. So the only contributor to the thermal expansion coefficient in the glassy state is the vibrational part due to the inharmonicity of the potential energy well. However, as we heat through the glass transition region and get into the liquid state, you see that there is a steeper slope here. That steeper slope is because the liquid has not only the vibrational part of the CTE, but also a configurational part of the CTE due to the ability of the liquid to rearrange its structure and to access different configurations in response to changing temperatures. And so in the liquid state, we need to consider both vibrational and configurational contributions to the thermal expansion coefficient. This leads us to define two different types of CTE. So if the CTE of the liquid, alpha subliquid here, has two contributions, we can write them as the CTE of the vibrational part. This is just measured through standard dilatometry, and plus the CTE of the configurational part. So the vibrational CTE plus the configurational CTE gives us the liquid CTE. This vibrational CTE is just the CTE of the glass. This is what we get when we measure the CTE of a glass through dilatometry. And now the question becomes, what is the configurational part of the CTE? We can see what that is if we go back to this volume temperature diagram. And when we compare fast-cooled versus slow-cooled glasses, the fast-cooled glass has a different configuration than the slow-cooled glass. And the property that we use to quantify that is the fictive temperature. So the fast-cooled glass here, if we draw the straight line from the glassy state intersecting the supercooled liquid state, we can drop this down to the temperature axis, and this gives us the fictive temperature of the fast-cooled glass. This reflects the configuration of the supercooled liquid that gets frozen into the glassy state. And for fast-cooled systems, that happens at TF2. For the slow-cooled glass, again, we take the tangent line from the glassy line here, see where it intersects the supercooled liquid, drop that down to the temperature axis, and that gives us TF1, which is the fictive temperature of the slowly cooled glass. So if you draw a vertical line through this VT diagram, that is at constant temperature, but you can see here that the volume of the system is increasing with increasing fictive temperature, even though the temperature is the same. In other words, in going from the slow-cooled glass that has a low fictive temperature to the fast-cooled glass, which has a high fictive temperature, at that same temperature, the volume increased because of the configurational differences between the slow-cooled and the fast-cooled glasses. And that is reflected in the change of the fictive temperature and going from TF1 to TF2. So what we need to consider then is how much strain that the glass experiences by changing the fictive temperature under a constant temperature. Therefore, we can define the configurational part of the CTE, alpha config, as being equal to 1 over the length times the change of length with respect to change in fictive temperature, dL by dTf, under constant pressure and constant temperature. If we wanted to get the expression for the vibrational CTE, all you have to do is swap the T and the TF. The vibrational CTE is dL by dt under constant P and constant TF. And for the configurational part, the derivative is with respect to changing configurations and therefore changing fictive temperatures under a constant physical temperature T and a constant pressure P. And to see how this works, if on the left-hand plot here, we have density as a function of temperature for a given glass. And what we can see is that if we measure the CTE of any of the glasses here, the vibrational part of the CTE of the glass is equal to the CTE from vibrations. And in this case, the slope here is giving us 42.3 times 10 to the minus 7 per degrees C. And you can see that independent of fictive temperature here, this is a fictive temperature of 851.3, 758, 735, 700. The slopes here of all these curves are all about the same, indicating the same vibrational CTE independent of the cooling rate. Now, the configurational part of the CTE is given here by this line in the upper right-hand corner. And this is obtained simply by measuring the density of these glasses that were formed with different fictive temperatures. So if you take these 4 different samples that all have the same glass chemistry, but have 4 different thermal histories and therefore 4 different fictive temperatures, measure their densities. Their densities are located here. These are the densities at room temperature. And then plot this on the temperature axis where it is the fictive temperature of the glass being plotted on that temperature axis. And therefore, what we get is the change of density with respect to change of fictive temperatures. And then converting that change in density to a change in molar volume and then a change in length instead of volume. The resulting configurational part of the CTE for this sample is 107 times 10 to the minus 7 per degree C. So we've got the vibrational CTE, which is measured through dilatometry, and this is the CTE of the glass. And then we have the configurational CTE, which is measured by preparing different glass samples with different fictive temperatures and measuring how the density changes with fictive temperature. If you take those 2 contributions to the CTE and add them up, what you get is the CTE of the liquid. So the CTE of the liquid is the vibrational CTE plus the configurational CTE. So what we do is we take this CTE from vibrations, add it to the CTE from configurations, and therefore the total CTE of the liquid, the line here with the steepest slope, is 149.3 times 10 to the minus 7 per degree C. And the nice thing about this is that we didn't need to measure the CTE of the liquid directly. You can get this entirely from glassy state measurements. So measuring the room temperature density of the glass for different fictive temperatures, and also measuring the vibrational CTE of the glass through dilatometry. These are all lower temperature measurements below the liquid state. And with those, with only those glassy state measurements, we can add up the 2 contributions to the CTE and get the total CTE of the liquid state. Now, why is CTE so important? One of the reasons is that it is a key governing factor for the thermal shock performance of a material. Now, if we want to consider how thermal shock happens, let's consider if you have a piece of glass that has a wall thickness shown here, so going from one end of the sample to the other end across the thickness. Initially, this may be at a constant temperature, so it's the constant temperature through the thickness. But if you take this at a high temperature and then quench it to low temperatures, the outer surfaces of the glass are going to cool faster compared to the interior of the glass. So upon quenching this from high temperatures to low temperatures, the surface temperature is lower on either side, and then the temperature in the center of the sample is higher. And then if you take the average temperature, that average temperature is given by TA. And what this means is that basically the outer part of the sample wants to shrink more compared to the inner part of the sample, and it is not allowed to, and therefore the inner part of the sample is pulling the exterior of the sample into tension, and that tensile stress is shown here on the gray shaded region. So initially, if this is a stress-free sample, there's 0 stress across the thickness, but after quenching it, there are tensile stresses that form in the exterior, and the integrated tensile stresses, the integrated gray triangles on either surface there, that integrated area matches a compressive stress that is in the surface. And so if you integrate across all of this, the integral comes out to 0. But if there are any pre-existing flaws or little micro cracks in the surface of the glass, by quenching the sample, you've just put those flaws into tension, which means that there are tensile forces acting that want to rip the material apart. And if there are flaws present, those tensile stresses are going to be amplified at the tips of those flaws. And that's why it is much easier to break a glass in after thermal shocking it, especially if there are pre-existing flaws on the surface. Now, the way that we calculate the stresses that are evolved as a result of thermal shocking is shown in the equation here in the lower left. This is equal to the temperature, the local temperature minus the average temperature. So how much is the local temperature varying with respect to the average temperature? If it's on the surface, it is lower. If it's in the interior, it is higher. So what is the temperature difference compared to the average? That gets multiplied by the thermal expansion coefficient. The thermal expansion coefficient tells you how much strain that the material undergoes per unit change in temperature. So this converts the thermal gradient into a strain gradient, and then that strain gradient gets converted into a stress gradient for a plate geometry by multiplying by minus Young's modulus over 1 minus the Poisson's ratio. So it's a temperature difference that gets converted to a strain profile by multiplying by the thermal expansion coefficient, and then that gets multiplied by minus E over 1 minus Poisson's ratio to give a stress profile. Now, that means that we've got different parameters here that govern the thermal shock performance of a material. A higher Young's modulus would be a higher stress and therefore worse. Poisson's ratio really doesn't vary by that much in glasses, so it's not a useful one to vary. The one that does vary by the most is the thermal expansion coefficient, because this in principle could be taken all the way down to 0, for example, in the case of ultra low expansion glass, or it could be even higher than 100 times 10 to the minus 7 per degree C. So the parameter that we can vary the most is the thermal expansion coefficient. And therefore, designing glasses with low thermal expansion coefficients is critical to improve the thermal shock performance of those glasses. Now, our glass great for today is Harold Rawson, who lived from 1927 to 2001. He grew up in England and graduated with a degree in glass technology from the University of Sheffield in 1947. He joined the British Thomson Houston Company, where he developed new glass sealing technologies for the emerging semiconductor electronics industry. In 1964, he joined University of Sheffield as a lecturer in the Department of Glass Technology, and he stayed there to earn his doctoral degree in 1973, becoming a professor there in 1975. And he made the original prediction that the optical attenuation of glass could be brought below 20 decibels per kilometer by reducing impurities. This was key encouragement for Charles Kao in his pioneering work on optical fibers in the 1960s, which led to Kao winning the Nobel Prize in 2009. So to summarize today's lecture, the thermal expansion coefficient of a glass is vibrational at low temperatures due to the anharmonicity of its potential energy wells. In the liquid state, the CTE has both vibrational and configurational contributions. Creations of non-breaching oxygens and larger sized modifiers tend to favor higher CTE. And thermal shock can result from rapidly quenching the glass. The way to reduce thermal shock is to lower the CTE of the glass. Next time, we are going to jump into glass technology. We are going to cover fundamentals of inorganic glass making. All right, thanks everyone for listening. I will see you next time.